Hello. In this episode, I shall return to the timeline to entanglement that I introduced in episode 18. And if you haven't watched that episode on the Solvay Congress and the Einstein-Podolsky-Rosen paradox, you should absolutely go back and watch that one first before returning to this one. Einstein was a proponent of what is called local realism, which insists that the results of measurement on one particle at a given location should not affect the results of measurements on another particle at a remote location. And this led him to insist that quantum mechanics is incomplete and has to be supplemented by a set of as yet unknown or hidden variables that specify the properties of each particle in the singlet pair. Well, in 1952, David Bohm uh, formulated exactly such a hidden variable theory in apparent contradiction to von Neumann's proof that hidden variables cannot exist. This led John Bell to re-examine the problem a decade later. Bell obtained his bachelor's degree in experimental physics from the Queen's University of Belfast and a year later a bachelor's degree in mathematical physics, followed by a PhD from the University of Birmingham, specializing in nuclear physics and quantum field theory. Bell was a proponent of de Broglie's pilot wave theory, and when he re-examined the Einstein-Podolsky-Rosen problem, he developed and he established an inequality which specified the minimum disagreement between the results predicted by local hidden variable theory and those predicted by orthodox quantum mechanics. This elevated the disagreement from a problem of mere interpretation, as had been previously believed, to a difference in the actual physics involved. John Clauser, along with Abner, Shimony, and Michael Horne, then refined this inequality, and Clauser then went on to perform the first experimental tests of this inequality, which showed that quantum mechanics, in its orthodox interpretation, was correct and yielded the experimental results. This was followed up in 1982 by a remarkable set of superluminal experiments by Alain Aspect and colleagues, where they changed the settings of the experimental measuring apparatus while the particles were flying from the source to the detector. And these experiments unequivocally confirmed that quantum mechanics gives the experimental results and not local hidden variable theories. These experiments were further refined by Anton Zeilinger, who went on to develop quantum cryptography, quantum computation, and quantum teleportation, as we call them today, culminating in the 2022 Nobel Prize in Physics to John Clauser, Alain Aspect, and Anton Zeilinger. I'm taking these quotes almost verbatim from the abstract of John Bell's remarkable 6-page paper, where he says the paradox of Einstein, Podolsky, and Rosen was advanced as an argument that quantum mechanics could not be a complete theory but should be supplemented by additional hidden variables. These additional variables were to restore to the theory causality and locality. In Einstein's words, but on one supposition we should, in my opinion, absolutely hold fast. The real factual situation of the system S2 is independent of what is done with the system S1, which is spatially separated from the former. Bell then goes on to say that it is the requirement of locality or more precisely, that the measurements on one system be unaffected by operations on a distant system with which it has interacted in the past, that creates the essential difficulty. Moreover, as I pointed out, a hidden variable interpretation of elementary quantum theory had been explicitly constructed by David Bohm in 1952. Bell pointed out that that particular interpretation has indeed a grossly non-local structure. John Bell showed that this is characteristic of any such theory which reproduces exactly the quantum mechanical predictions. Bell then goes on to mention for Neumann's proof that hidden variables cannot exist, and in a separate paper he shows that this proof, although mathematically correct, rests upon an invalid assumption. Bell showed that no local hidden variable theory can reproduce all of the statistical predictions of quantum mechanics. Bell considered the Gedanken experiment of Bohm and Aharonov, which is a variant of the Einstein-Podolsky-Rosen Gedanken experiment, in which a pair of spin half particles is prepared in the singlet spin state and moves freely in opposite directions. Measurements can be made on selected components of the spins, sigma 1 and sigma 2. If measurement of the component sigma 1 dot a, where a is some unit vector, yields the value plus 1, then according to quantum mechanics, sigma 2 dot a must yield the value minus 1 and vice versa. That means if you measure the spin of particle 1 to be up in the z direction, that of particle 2 has to be down in the z direction. According to Einstein locality hypothesis, if the two measurements are made at places remote from each other, the orientation of one measuring apparatus cannot influence the results obtained with the other. So whether you measure the z component or whether you measure the y component or the x component. So you don't need to measure the same component of the two particles, and this is what makes the difference. Since we can predict in advance the result of measuring any chosen component of sigma 2 by previously measuring the same component of sigma 1, it follows that the result of any such measurement must be predetermined according to the local realism assumption. Since the initial quantum mechanical wave function does not determine the result of an individual measurement, this predetermination implies the possibility of a more complete specification of the state. Let this more complete specification be effected by means of parameters lambda, which are the hidden variables. The result of measuring the sigma 1 dot a is then determined by a and lambda, and the result b of measuring sigma 2 dot b is determined by b and lambda. Thus, a of a and lambda can take the values plus or minus 1, and similarly b of b and lambda can take the values plus or minus 1. The vital assumption is that the result B for particle 2 does not depend upon the setting A of the apparatus for particle 1 nor A on B in the local hidden variable formalism. If rho of lambda is the probability distribution of lambda, then the expectation value of the product of the two components sigma 1 dot A and sigma 2 dot B is given by probability of A and B equals integral over d lambda, rho of lambda, A of A and lambda times B of B and lambda. This is the result obtained from the local hidden variable theories. Whereas the quantum mechanical expectation value for the singlet state is expectation value of sigma 1 dot A times sigma 2 dot B is minus A dot B. This is the quantum mechanical result. Bell then showed that this result is not obtained with the Einstein locality condition. I shall not go over the full proof of Bell's theorem. But if you're interested in it, you can pause the video at this point and follow the proof that I've outlined here. The net result is that the result predicted by the local hidden variable theory is different from the quantum mechanical prediction. Bell then derived a lower bound for the disagreement between quantum mechanics and local hidden variables. Okay. Again, I shall not go through the derivation in detail, but if the disagreement is given by this epsilon, then this inequality holds. That is, for that epsilon cannot be made arbitrarily small. Okay. Thus, the quantum mechanical expectation value cannot be represented by the local hidden variable expression. Bell's conclusion then is that in a theory in which parameters are added to quantum mechanics to determine the results of individual measurements without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. Okay. This is directly contradicting the local realism assumption. Moreover, the signal involved must propagate instantaneously so that such a theory could not be Lorentz invariant. And here's the source of Einstein's discomfort with quantum mechanics, because Einstein's relativity theory had established that there is no action at a distance, and that signals, physical signals, propagate with the velocity of light. Of course, the situation is different, Bell goes on to say, if the quantum mechanical predictions are of limited validity, experiments in which the settings of the instruments are made sufficiently in advance to allow them to reach some mutual rapport by exchange of signals with velocity less than or equal to that of light. That is, while you are setting up the instruments, maybe one part is somehow communicating with the other part, and therefore, when you perform the measurements, the experiments on the two parts are correlated in just such a way that to give you the quantum mechanical result. So this is the possibility that has to be excluded, and this was done, as I will explain, by Alain Aspect's superluminal experiments. Experiments of the type proposed by Bohm and Aharonov, in which the settings are changed during the flight of the particles, are crucial. So Bell actually suggests that such experiments where the settings of the measuring apparatus are changed during the flight of the particles from the source to the detector, that such experiments be performed. Bell thus took what was hitherto a philosophical debate over the interpretation of quantum mechanics and turned it into an experimental question. Bell's theorem points to a decisive experimental test of the entire family of local hidden variable theories. The correlations between a pair of entangled particles can be used to differentiate local hidden variable theories from quantum mechanics. So no longer shut up and calculate, this has real physical consequences. The key, however, is to ask different questions of the two particles. So not just if A is spin up or spin down and is B spin down or spin up, that we know the result. If A is spin up, B has to be spin down. If A is spin down, B has to be spin up. That's the same in local hidden variable theories and in quantum mechanics. And but we can ask if A is spin up and spin down in the Z direction, then what is B in the X direction? Again, if A is spin up or spin down, then B will be 50% of the time pointed this way and 50% of the time pointed that way. Again, the result is the same in both quantum mechanics and in local hidden variable theories. But now if B is oriented at a different angle, that's when the differences between local hidden variable theories and quantum mechanics shows up. The actual experiment performed by John Clauser involves not measuring the spins of an entangled pair of particles in the singlet state, but it involves sending a pair of entangled photons that are then sent to different polarized filters. So here you have an atom which emits a pair of entangled photons, and here are two polarizers. This one is oriented vertically, whereas this one is oriented at an angle. If both particles are sent towards filters oriented in the same plane and one goes through, then the other will also definitely go through. If they are at right angles to one another and one photon goes through, the other, so if one is oriented vertically and the other is oriented horizontally, and if one photon goes through, then the other will definitely not go through. And these are again the same in both quantum mechanics and in local hidden variable theories. The trick, however, is to measure with the filters set in different directions at skewed angles, as then the results of quantum mechanics and hidden variables with local reality differ. How often both particles go through the filters depends upon the angle between the filters. John Clauser, Michael Horne, Abner Shimony, and Richard Holt proposed a generalization of Bell's theorem. They derived a constraint on the statistical occurrence of coincidences in a Bell test, which is necessarily true if an underlying local hidden variable theory exists. And this constraint is that the modulus of S has to be less than or equal to 2 according to a local hidden variable theory, where A and A' are the detector settings on side A of the measuring apparatus, B and B' are the detector settings on side B, and P of A and B is the quantum correlation of the particle pairs, that is the expectation value of the product of the separate outcomes A of A and B of B, that is of one setting of the measuring apparatus A and another setting of the measuring apparatus B. The Clauser-Horne-Shimony-Holt inequality is violated both by quantum mechanics and by experiments. Quantum mechanics predicts that the modulus of S is greater than 2, contradicting the local hidden variables theory for systems prepared in suitable entangled states and the appropriate choice of measuring settings. The maximum violation predicted by quantum mechanics is known as Tserelson's bound and is obtained from a maximally entangled state known as the Bell state, for which the modulus of S is equal to 2 root 2. Violation of the CSSH inequality was confirmed by John Clauser and Stuart Friedman in 1972. This shows John Clauser with his measuring apparatus. This is the optical version of the Einstein-Podolsky Rosen Bohm Gedanken experiment by Alain Aspect and co-workers. Here, the coincidences between the photons arriving at detector 1 and detector 2 after passing through the polarized filters A and B, this coincidence is measured. Recall John Bell's claim that the signal involved must propagate instantaneously. To rule out the possibility of some physical signal being exchanged between the two detectors with a velocity less than or equal to the velocity of light, these settings of the polarizers are not predetermined. The orientations of the polarizers are set after the two photons have been emitted by the source and while they are on their flight to the polarizers. So in Aspect's 1982 optical version of the Einstein-Podolsky-Rosen-Bohm-Gedanken experiment, a source emits a pair of photons. Measurement of the correlations of linear polarization are performed on the two photons belonging to the same pair. Aspect et al. Devised a mechanism that could switch between the different settings of the instrument after the entangled photons had been created and emitted from their source, so that the system would not contain any advanced information that could affect the results. So whether the polarization is whether this polarizer is in the vertical setting or in this setting is determined after the photons have been emitted. And likewise for the other polarizer. The filters were 6 meters apart, and switching between the two channels occurs within 10 nanoseconds. This time delay is small compared to L by C, which is 40 nanoseconds. Thus, a detection event on one side and the corresponding change of orientation on the other side are separated by a space-like interval. But interactions mediated by physical fields cannot propagate faster than the speed of light, so there is no physical signal that is propagating from one detector to the other. So what do the experiments show? These are the experimental data for different relative orientations of the polarizers, and the dotted line shows the quantum mechanical predictions. So we see that the results of all these experiments are incompatible with local hidden variable theories, but agree with quantum mechanics. Just over a year before the Nobel announcement, we nominated Dr. Alain Aspect for an honorary doctorate from Shiv Nadar University, and I seconded his nomination, and we were very gratified that he accepted and delivered an address at our 6th convocation in 2021. That brings us to what is called the second quantum revolution and the work of Anton Zeilinger. To address any residual doubts about correlations within the measuring apparatus, Anton Zeilinger and colleagues created entangled pairs of photons by shining a laser on a special crystal and used random numbers to shift between different measurement settings. Here, signals from two distant galaxies were used to generate random numbers that control the orientations of the filters and thereby ensure that the signals could not possibly affect each other. Entangled quantum states have now been demonstrated between photons across tens of kilometers of optical fiber and also between a satellite and a ground station. Consider an entangled pair of particles traveling in opposite directions, and one of them then meets a third particle in such a manner that they become entangled. They then enter a new shared quantum state where the third particle's original properties have been transferred to the solo particle from the original pair. This transfer of an unknown quantum state from one particle to another is called quantum teleportation and was first demonstrated by Anton Zeilinger and his colleagues in 1997. In 1998, Zeilinger and his colleagues next used two pairs of entangled particles. Here, particles 1 and 2 form one entangled pair, and particles 3 and 4 form another entangled pair. One particle from each pair, here particles 2 and 3, was then brought together in such a way that the undisturbed particles in each pair, that is particles 1 and 4, become entangled despite never having been in contact with each other. It's only particles 2 and 3 that are in contact with each other, but because of the pre-existing correlations between 1 and 2 and 3 and 4, now particles 1 and 4 become entangled with each other, although they never came near each other. In this way, two particles that have never been in contact can become entangled. We will stop here for today and continue next week with Professor Bindu Bamba's journey into quantum computing. See you then.